This is my graph. It's 24 hours of data, around 17,000 data points per line. So the detail is present. There's a scan or a data point every 5 seconds. So for every minute, that's roughly 12 readings. And I think that's dense enough for a wood stove, especially a science project around a wood stove. We don't change things much in 5 seconds. So I'll go to the next graph. This is 10 hours of data. Now, 10 hours of data is a little easier to see. You can pretty much tell when I open the door or put a piece of fuel on. I don't think you could put much fuel on this stove without me seeing it in this data. We have two things presented. One is the opacity, which is the blue line, and then we have the color shift, which is the orange line. One of the channels I get from the sensor is IR, infrared, and it wasn't a channel I was previously looking at very closely, and I wondered if there was any data in the IR signal that could be useful. Well, we get a pretty clean signal with a delta of about 200% at times. So these are near the times I'm opening the door. So it clearly, in the data, you can see that something is happening in the wood stove, solely looking at the IR channel. Now, we'd have to filter this a bit. However, I am kind of intrigued that there is data here. We can combine it with the other channels. It could be that the IR drops in this case. I'm not sure which direction I've got this programmed. I was simply looking for a change, a percent change, and it seems to go in one direction, but I'll bet you it is a reduction in infrared. We need to look into this closer. This graph is 3 pounds of wet wood. I put it on at 8.5 hours, and for the next 0.2 of an hour, that's about 12 minutes, we get significant opacity and color shift. And I want to talk about the slight differences there are between opacity and color shift. Color shift is Tyndall scatter that adjusts or scatters off blue light, and so we get more red light. So it's a shift to the red. A shift to the red is a shift in color, and we measure that in nanometers, and we have roughly a 30 nanometer change at 8.6 hours. From there, it almost goes back to zero, I'd say 10%, by 8.7 hours. Whereas opacity drops below 20% just before 8.6 hours, and then to about 5 at 8.7 hours. So this gives a good idea of how much time a piece of wet wood contributes to smoke production. From, I'm going to say, 0.5 to 0.6, we've got a pretty good, that's 6 minutes of pretty darn good smoke output. And not one data point under 20% for that. And we get a reading every 5 seconds. So we can say with certain certainty, get my certainties right, that for about that amount of time, we had no readings under 20% or 20 nanometers. But then by 8.8 hours, we're burning clean again. I mean, really burning clean at 8.8 hours. It doesn't go above 10%. So this is a really good chart, and it's a close-up. It shows we were running really clean till I put this piece of wet fuel on, and then things got smoky for about 12 minutes. Now this is the temperature of the wood stove. So the blue line is the shell, and the orange line is the gases going up the stack, and the blue-green line is the heating air that the stove produces. So anything over 100 degrees, and you're getting nice warm air off the stove, and it's putting out about 20 CFM of nice warm air into that room downstairs. The exhaust temperature is always something we're interested in, and one of the indicators I can see in the data is where it drops significantly down to the stove temperature. That's the times that I have the door open. So I got the door open to break up the fuel, to make space in the wood stove, to move things around so that it gets air to a different part of the fuel. And I also put fuel in when I open the door. So I could be doing both things. When you see the temperature go up afterward, it's pretty clear I was putting fuel in. So you see that pattern where you get a drop in exhaust gases and then a rise in stove temperature. It's an indicator that I'm putting fuel in. There's also an associated bump with the green line showing that the heating air of the room was higher at times. I like it when it's 110 to 125. The ROR chart is used when I want to see how the system is responding to the combustion air that I'm giving it. I'm giving it a certain pattern of combustion air, and I want to see that the stove is responding correctly. We have a rate of rise up to 20% in the first half hour, up to 20 degrees per minute. That's a pretty steep rise in temperature, and we want to keep that under control. However, I'm not worried about 2025, and occasionally I might see 30 for a brief period of time, but this stays about 10. It does get up to about 20, and then when you see it drop down, that means the stove just isn't getting colder. It would have to drop below zero before the stove would be cooling off. So that downslope on the back side of the curve is simply the stove not getting as hot over time. It's still heating up, but it's not getting as hot as it was on the steep part of the curve. So this is transmission rate. I have programmed the smoke sampling unit, the Octaring, to send off a signal every 5 seconds. And for the most part, it did that. There are a couple anomalies. You see an occasional 10 seconds, but around 4 hours, we also have a 40-second delay, and I'm not sure what happened there, but I can keep an eye on it. We have a 25-second delay out around 9 hours. So it could be during high smoke events. It could be for some other reason. I don't know at this point, but at least I know they're present. 17,000 data points in 24 hours, and we can catch little time travel events.